and of course, AI and edge computing. All summit sessions will be available on demand, and each of our presenters also has a microsite loaded with more opportunities for skill building and professional development. We also have prizes. Get a giveaway entry each time you register for a live session for your chance to win some All About Circuit swag or a Pick It Yourself grand prize. And now it's time for today's keynote, brought to you by Mouser Electronics. Delivering the newest electronic components for design, Mouser is your global authorized distributor for millions of components from over 1,200 leading manufacturer brands. Jumpstart your designs at Mouser.com. Today, I'm joined by Christian Eder, Director of Market Intelligence at Congatec and a key voice behind open embedded standards like ComExpress, SMARC, and ComHPC. We're going to dig into the importance of open standards and how edge AI, advanced compute, and security concerns are reshaping embedded design. Christian, thanks for being here. I'm really looking forward to this.
My pleasure.
I'm curious, how did you first get into engineering and technology, and what gets you excited today?
Let's say maybe it goes back to my father. I was a really hands-on technician. He always wanted to write some, let's say, patents and whatnot. Never succeeded on that, but that brought me maybe a bit to technology. And then later on, after I finished school and went to university, so I was in between, should I go more for architecture, the construction stuff, which is more creative, or into electronics. I always loved audio electronics, so amplifiers, building amplifiers, speakers, and that stuff. And by the way, I still do that. I did it again, actually. And then it was more or less by rolling the dice here that I went into electronics. But never regretted that one, actually. And it was a great time being at the university. I'm an electronics engineer here. But in fact, I never worked as an engineer. I wanted to, but say it just happened, and I went into product management, product marketing at my first job, more or less by accident. But then I loved it at the end. So it's this job which is technology, but also the use of the technology. And that made me, was quite fun. And at that time I did work. It was at, by the way, it was at Contron, was my first job, so more than 30 years ago. And I worked a lot with Marcom, actually. And I was really fascinated. They asked me, what's special about your product? Can you write something? And I wrote about maybe a small chapter just with facts, actually. And then I gave it to an agency, and they made a paper like that out of it. And finally, in the newspaper, printed version, it was again my abstract at the end. So I thought, maybe this could be done better, and maybe this was a key event or key learning, actually, is that I went more and more into the communication side of things. I still understand the technology, but also did a lot of communication stuff.
What is your take on how marketing and product management roles should engage with engineering? Any tips for being successful there?
At least a basic understanding, I would say. So and also some key thing. I had students, let's say, marketing students coming from the University for Economy, and it's their dream job to get my job. Actually, it's being marketing managers. That's great, of course. That's the greatest thing. But how could you do this as an engineer? Actually, and at the end, it's about understanding things. And I think the best thing what you can do is have a combination to understand both sides of the world, actually. So in Germany, there's some university courses. If you do engineering, then you can do some economics on top, or the other way around. So I think that's the best thing, to have a look to both sides. You understand both sides a bit, at least, or a bit more.
What was the early environment like for embedded computing? When you started, was this kind of a new concept, or how are people thinking about and using this sort of technology?
At that time, everything was, let's say, much bigger, not as powerful, much more power hungry. So the embedded devices couldn't get that small. Actually, it was really big cases of computers. So notebooks have not been there. Actually, they have been the first mobile computers. It was something in the whatever 10-15 kilo range with integrated CRT tube monitors, and those have been used for embedded applications. I remember one use case here for a PLC programming device. And in order to communicate with the PLC, it needed a full-length card to be plugged into a mobile computer just to communicate with the PLCs, actually. Everything was expensive but necessary. So it was the mobile applications, the embedded applications for test and measurement, for PLC, for industrial automation, and the machines which did run, let's say, a production line had been rack mount computers. Everything was about rack mount. 19-inch was the choice. And it started at that time in the 90s that the smaller computers had been invented. So when there was a power consumption came down and we reached something like whatever 20, 30, 50 watts or so, that computers could get smaller. And this was a start to integrate those computers to whatever devices, actually. At that time we had this Eurocard PC, something like 100 by 160 millimeters slot cards. Everything was kind of slot PCs, this ISA or e-ISA cards. This was the beginning of the standard. I was attached somehow. I never was involved into generating those standards, but to use those and also to motivate the engineers to produce or to develop something compatible for these use cases, to be exchangeable. That was also a use case at that time. It started this exchangeability a standard that you can't mix and match between different vendors. That's it. And this was also a basic idea.
So how willing have people been historically, engineers been historically, to adopt open standards versus kind of developing their own proprietary standards that works well for them and maybe not for anyone else?
I think there was a mind change thing. So I remember when I was at Congatec later on, so we started the ETX standard, the first computer module standard. And I was convinced, and I was discussing with my boss, so why should we make this an open standard? So this is our unique selling proposition. Only we can do that. And then we had a happy discussion, and then that was the key message, what I learned. Of course, if we did a small Congatec at that time was a company with 60 people or so, of course, a small company only can sell to small customers. That's the end. So it must be somehow leveled. That's the end. But we actively approached Advantech at that time, big Advantech, still big, to follow this standard as well, to follow this ETX standard. And I did. And out of that, we had the chance, of course, to sell to much larger customers, because it was no longer a risk for them to buy at a smaller company. Because if that small company fails or gets out of business or whatever happens, they still have the second source from this large supplier, from the Advantech in this case. This was just a starting point, and that was, okay, that makes sense. And this whole idea developed quite a lot. And the whole computer module market, which is something like a 2 billion market these days, or 3 billion in the meantime, I don't know exactly, was just based on this idea, actually. There have been the same time other module concepts from other vendors who with the idea, this is just mine and you can only buy it from my side, that's my USP. And they all failed. They have been, some of them have been technically even nicer and better, but they never succeeded, actually. It was the standard, the open standard, which made it. And this was my key learning. And then I was part of many open standard projects.
I think what I hear you saying is that standards really help provide kind of almost like supply chain or technology chain security for especially large companies who are looking to integrate these into their designs.
Yeah, overall, so just think about, let's say, 100 years back or so. So Industrial Revolution, and at that time, if you want to build a, let's say, steam engine or something like that, you need screws. But there was no standard for screws. That means the company building steam engines had to make screws, bolts and nuts and whatnot, all of that, based on their own standard, because there was no standard actually. They had to make those. Of course, it's a it's a unique technology to make all of this. And we see standardization nowadays, or long time ago, if you want to buy a screw, yeah, it can be complicated if you're in the US or in or the rest of the world, but at least there are two standards. Uh, Europe speaking here, actually, I go to a shop and say I need a screw M5, and I get it, and I have no doubt that it will fit to whatever my application, and the counterpart is something else coming from somewhere else. It will fit. That's helped a lot because the companies do not have to take care about this nitty-gritty stuff. They can focus on the real stuff. It's the same with the embedded computer stuff. You don't have to handle the complicated stuff here with memory interface and with the chip vendors and whatever, and how to reset and power all of that. You just take a computer module on a higher standard. So you have some clearly defined mechanics, even cooling interface. You have these signals here on a high level. Here's a USB, and here you feed it with 12-volt DC power, and it goes. And
yeah, it's a beautiful thing.
yeah, you're much faster. It's the design is much faster. It's much lower designer risk actually, and you have the complete second source idea. It's the same like going to a shop and buying a screw or buying a ComExpress or ComHPC module. You find different vendors, and yeah, it's a more complicated part compared to a screw, and there are more details to be thought about. But in general, you have the chance to switch technologies, to switch vendors, to be flexible, and don't have to do a full design from scratch. Each time the technology changes. And we know chip technology changes a lot, extremely fast, still, or even more extreme than looking to the past.
So let's talk a little bit about the general environment of compute on module, or we'll call it comms a lot. Congatec is a industry leader in this space. Who is using this sort of plug-in compute, and what sort of applications are those going into?
It's used, let's say, almost everywhere, I would say. So we do have applications, let's say, starting with casino gaming. But on the other hand, it's also the same module, the same piece of module is also used in an ultrasonic medical device. So this means the module itself is general purpose. It goes also to a robot controller. It goes, I think, the real-time controller to control gas engines, so gas turbines for energy. It goes into edge devices. It goes into servers here in more on edge servers. We're not typically in the data center server stuff, but let's say almost everywhere. Of course, we have some focus points. Robotics is a strong one. Industrial automation in general. So medical. So those are the, let's say, the key markets, but also, let's say, transportation, test and measurement, entertainment. We mentioned that, even, let's say, professional audio and video. Now with video recording, maybe there's some Congatec modules somewhere in the stream from here to the data center. I don't know. That's the beauty of embedded computers. You don't see them. They just do their job, and you don't see them. And there are lots around.
What is maybe the most surprising or unusual implementation that you've seen of embedded compute?
I heard from my colleagues that even on some satellites there are some modules here. I know there's a lot of radiation, but obviously they managed to do the radiation. Of course, extreme applications are in, let's say, aerospace here, helicopters. So it's heavy. Sounds easy, but the vibrations, it's random vibrations. You don't have the same frequency. It's always changing. So from the point of vibration, helicopter is one of the worst.
Interesting.
That's from the environment side. But one thing which is kind of fascinating is, of course, all the possibilities we have with AI. So we work with a university here to do AI analytics here of ultrasonic scans of brains, actually, while doing brain surgery. During surgery, actually, to find out if they have to take some more of the cancer, or they already reached everything which is in head. That's of course fascinating to see how technology can save lives. Maybe one of the most spectacular one was during COVID. We had been able to supply ventilate company doing these ventilation machines actually, and also was really thousands of units we have been shipping out actually to make those ventilators. It was a customer which bought maybe hundreds or so months, and it went to thousands of months and above. And it was not easy at that time with all that supply to get all the components, but as this was really critical, so we have been able to do that. That made us proud, of course, to be able to help someone.
Absolutely. And it's a very, very noble cause in a very difficult environment too. The supply chain in 2020, I hope to never re-experience that moment.
No, we don't need that again, actually.
Yeah. Can you give us a little bit of history of standardization of compute? So I think we see, the role of it. It's important, but it's also kind of this hidden technology. But it didn't just appear, in the last couple of years. It's been something slowly built up over time. Could you maybe start with like ETX and talk us through what that history's looked like?
Yeah, of course. For me, ETX was the first one. So export ETX was the very first one. It was back in 1999, actually, last millennium, actually, a while ago. And as I mentioned before, this was the first computer module standard which became successful. And after this successful introduction here, then next one which was founded was ComExpress, in fact, in parallel with also the founding of Congatec at that time here was XTX. So XTX was initiated by Congatec, was the extension of ETX. ETX was still isobus based, and we just removed one of the four connectors which only had the isobus and brought up PCI Express lanes. And that was let's say, kind of compatibility thing. As long as you don't use the isobus, you could use this module directly, and you could upgrade your carrier ports with the PCI Express bus. In parallel, ComExpress came up here, and that, in fact, developed itself to be the most successful standard ever. So I was editor for this specification for a while. So that was my first, one of my first roles actually in standardization, to be editor. But I learned a lot as an editor because what's the English saying? I think it's the power of the pen. So editor, you can influence things. Of course, not decide. It's a democratic approach, but you can trigger things and convince people to go the right direction. That's what I did also later on with the SMOG specification. SMOG specification was originally created by Contron that time. Let's say one of our market enemies, I would say, and it was purely defined for special kind of applications, I would say, with a lot of special pins and whatnot. And then I came to place as an editor, and German as well, I guess, yeah. And I was able to influence the spec and to remove everything unnecessary and make a very successful standard out of it. So I'm quite proud about this. That SMARC with the release of 2.0 really became a successful standard. It's still growing like hell. That's the smaller form factors. Of course, with ComExpress in parallel here, that did develop over time quite a lot. There have been some releases, but finally we reached the limit. So the ComExpress connector itself was specified to maximum speed of PCI Express Gen 3. And as we know, the PCI SIG already works on Gen 7. So it's generation by generation, it doubles the performance actually. So this was obvious that new technologies are coming which cannot be supported. It was before those chips with higher generations of PCI Express went to market. We started this activity and created ComHPC.
So tell me about ComHPC. What was the original intent behind it, and why does it exist? Because it's a big one.
Yeah, it's just to be faster, actually, just to keep pace with the chip technology. This was the original motivation, and to continue with the success of ComExpress. So ComExpress had different sizes and let's say different pinouts, and this was also reflected in ComHPC. So we started with the client and the server platforms. So with much more headroom, let's say it's about double amount of pins, double amount of interfaces, I would say. So up to 64, 65 PCI Express lines, for example, for the servers. Being larger in order to allow for higher power consumption, because you need to have cooling, and the server chips are quite big actually, and we could scale up to, or we can scale up with the servers up to something like close to 500 watt of power.
Sure.
ComExpress was limited to, let's say, maximum of 188, I guess, was the highest. So much more headroom, double amount of interfaces, and the speed, let's say, about 8 times the speed of the interfaces. So that's a motivation. Performance, and performance actually. Chip-based.
The big three.
But
Yeah.
later on, we found out, but size also does matter. And it was the same story, exactly the same development as with ComExpress. ComExpress later on defined a mini type, which is smaller, with less features, let's say, and we did the same with ComHPC. The ComHPC Mini only has 1 instead of 2 connectors, just 400 instead of 800 pins, and it's much, much smaller. And in fact, it's the version which starts like a rocket. So it goes crazy. Those projects are really the first ones to come to place, actually. The latest, the definition which we created lately, let's say, is the one which starts up the first. So that's funny, but nevertheless, although the server and clients are doing a great job, but the Mini is outperforming.
So this is like a server chip on a module board, and that snaps into like a larger server carrier board motherboard.
Exactly, it's the same idea as with all other standards. Let's say you do have a standard module, a standard connector with a clearly defined feature set, even with a mechanical cooling interface on top, call it a heat spreader. And this thing goes to a customized carrier board. Let's say the module itself you cannot use. It's just stupid because you cannot connect a single cable. It's just board-to-board connectors, and you need to create the counterpart. That's the counterpart, we call it a carrier board. There are standard carrier boards available, but usually it's a customer or we creating a carrier board based on this application demands. So it means there's a specification, I need this and that interface, this connector here, this connector there, whatnot, and this can be done in a comparable, easy way. If you, let's say, buy the chips and make a complete design with CPU and memory and whatnot, it takes forever. And a lot of details you have to take care about, and not talk about signal integrity with the higher speed. So it's complicated. With this, you have on a higher level, create your carrier board, which can be quite easy. Can also be complicated depending on your particular requirements. If you have, let's say, complete motor controller on top, special electronics, or like in medical ultrasonic, so that typically you have the signal improvement here from the very noisy signal from the ultrasonic heads, have this on the carrier board, which no standard computer can do that actually. That's done on the carrier board, and then that data is fed into the module and being analyzed and displayed here. And it's the separation between standard and custom. So which means you can make a custom computer based on a standard, and the customization is, let's say, much more simpler than doing a complete design.
So in the medical example, the board is essentially kind of pulling the analog data, turning it into usable, processable digital data, sending that through into the module. The process happens, the decisions are made, and it sends the results back out.
Kind of actually. So the pure analog part is on the carrier board. So the transfer to make it, to improve the signal quality and to make it digital, that happens on the carrier board. And then the data is sent to the module here for the computing. And that's a part where more and more Signal improvement also happens here, utilizing the GPUs. So the digital signal improvement needs a lot of compute power, and the graphic engines do have that compute power. That's being utilized. In the past, I used a lot of DSPs to do that on the carrier board, so that brings down the cost. And the next big thing is that AI comes to place. As mentioned before, it's to give at least a helping hand that, let's say, see, AI is also watching, let's say in this ultrasonic scam thing. Hey, I saw something, you better watch closer to this area. I saw something unusual. That's why, and then the operator can look deeper, can look to more details actually, and that's the beauty of AI. And we see that AI in X-ray, for example. So for many years actually with AI improvements, so you can work with just a fraction of the power for the radiation actually. So that it's less less harm to the body with this radiation actually, and you can get. There was a number from some years ago actually. I think it was just a quarter of the radiation power could bring the same or even better result as without AI and full radiation at the time. And that's also a couple years old. I'm pretty sure it went even better these days.
I definitely want to dig more into AI and like centralized versus edge computing. But first, I think you've been a bit humble here on the COM-HPC spec. For lack of a better term, you've kind of fathered this spec, right?
Yeah, absolutely. So Congatec started this one. I was involved in talking to Contron, talking to Advantech, ID-Link, whatnot, to all the other vendors to start this work group. And then, of course, it's a democratic process within PicMig that some votes have been taken. And I was voted here to become chairman of this group. And that's the first time being, let's say, chairman for a big working group. And it's, in the meantime, I think it's how much? I think a minimum 200 conference calls or so with all the specification and specification parts. I really spent a lot of time into this one. And of course, spending that much time with your baby, of course, it's part of my heart. But it's a big challenge actually to bring the things together and to avoid mistakes we have done in the past. Just looking back here, when we created ComExpress, there was no second source for the connector. It was a single supplier thing, and it took quite a few years before second sources came up actually, and we avoided that. We worked here with Samtec as a supplier, and Samtec guaranteed to license this under fair conditions to third-party vendors. And there, in the meantime, there are, I think, 3 or 4 extra vendors here for this connector. So we avoided that mistakes. Also, we avoided to bring up technology which is coming from a single chip vendor. It also happened at ComExpress at the beginning. So this is truly an open standard, which is not influenced to one or the other side, that you cannot do this chip technology, you have to use that one, whatnot. And it's truly open here for other platforms, for other technologies, chip technologies. It's not just x86, which is Intel, AMD, and some others, but also there are also seen some modules here about with FPGAs. You can even make accelerators, purely AI accelerator cards, because it's also can operate in a slave mode, like a graphics card or extension card. So there are ARM designs ongoing on COM-HPC, especially on the Mini actually. So it's really open, and that's why it will have a great future. It's future-proof. It does support up to PCI Express Gen 6. Gen 7 is just in the works. We will see. Going to be a new challenge, but so it's far beyond the technical capabilities the chips have today. But let's say within the next 2, 3, 4, 5 years, there will be chips to really outperform the COM-HPC performance, and that's, let's say, a minimum 10 times the performance you can get out of COM-Express.
What were some of the challenges or roadblocks? You already mentioned, suppliers, and earlier you alluded to heat spreading as well. What were maybe some of the unusual challenges or hurdles that it took to get this spec out the door?
It took a lot of time to do all this simulation for signal integrity with this growing speeds and clock rates. So when I was I learned engineering at the university. Digital was high and low, and in the meantime, everything is high frequency. It's a different world actually. With this speed we're talking, it's it's really crazy, and without a proper simulation, you cannot guarantee things. And the beauty of the spec is it has really detailed signal integrity information. It gives you clearly advice how to do the routing. So what's the maximum trace length? And if you need more trace lengths, then you can switch to better PCP materials, to low loss materials. We even have calculations. What's the trace length if you use this material or that material? The low loss materials are more expensive, but you get more performance out of it. As usual, you get what you pay. But you should only pay what you need. So that's the other thing. and that gives really clear guidelines for the complex technologies, and it's really helpful to make the complex easy. So as just like Janine mentioned before, our Congatec idea is fully behind that, to simplify the use of a better technology in order to do the complicated thing on the module and make it fairly easy to create a solution based on the module. So that's everything we're behind. And the standard is in line with our company philosophy.
800 pins. When I heard that and read that, I was my first impression was that's too many. Why are we going hundreds in a world where everyone's just like, just make it a PAM4 or PAM8 signal and make it small.
And it's already, so with PCI Express Gen 6 is PAM4 already, even, but which means it's with this we can have up to 64 PCI Express lines. But there's silicon visible, especially on the server side, which have 128 or even more PCI Express lines.
Okay. That's a lot.
Yeah. There's always more, let's say. You cannot do everything, but those are chips which are, let's say, data center chips, that stuff, actually. But there's not a clear border, actually, that's floating in between. What can be brought onto something like a COM-HPC? And the differentiation, I guess, between COM-HPC and a blade for a data center is where you're going to use it. So data center, of course, you have clear climate control, you have cooling, you have whatever stable power, all of this. You don't need, let's say, something like extended temperature range, what you need for an edge server. So that COM-HPC stuff was designed for edge applications, which means at the edge, you might not have an air condition. So it might be somewhere, let's say, out on the road or in a production facility or whatnot. I never know exactly. It can be quite warm, can be quite cold, depending where you are. So if it's something whatever at the Mexican border, it can be quite hot. If it's a truck in
the Canadian border, it'll be quite cold. So let's talk, edge versus server compute, data center compute. Like you mentioned, data center is just going to be hot all the time, but on the edge, you have a whole range of environmental conditions. What sorts of trends are you seeing in terms of what's going to be computed centrally and what's more happening on the edge?
Yeah, there are a few aspects actually you have to think about. Of course, some things are and will stay at the data center, no doubt. But some other things must be computed locally. Just let's say, think about your autonomous functionality in your vehicle. That's not our typical application, but you don't want that the vehicle has to send all the data to the data center and give the side back. Yeah, you better brake now, because if you lose connection or the data comes a bit late, that's bad. And it's also we don't have the bandwidth, let's say, to transmit each and every data to the cloud. Just think about all of the cameras which are around. Those must be analyzed locally somehow at local servers or sometimes directly at the cameras, and they only send something, let's say, interesting or something interpreted. So if there's an issue, they send information to the cloud, and then the reaction will be there. But it's also about, let's say, real time. If you have a machine being controlled, and this must happen in a definitive reaction time, actually. So all this real time computing stuff. So whenever it's real time, you cannot connect it to the cloud. And which goes on top and very, very actual, I think, is data privacy. Maybe you don't want to send each and everything to the cloud, even if it's possible from a technical point of view, but just on cybersecurity thing, and that's a big, big thing actually. We as Congatec are very well prepared here for all these cybersecurity regulations which are upcoming, not just in Europe. I know it's same or quite similar in US with all these regulations. And for example, our complete engineering process is already here cybersecurity approved. We have some certifications and whatnot. That's a big, big thing actually. It's coming from the legal side and it helps that. Again, coming back to this client server thing here, of course, if you can keep the data locally, it's more safe, I guess. So it's one more issue if you transmit it over a public network. That's always a thing. And it's the real-time dynamics, the legacy, that stuff. And another trend, which of course, computers are getting more and more powerful. So low power, and we see a strong trend in AI computing. So each and every chip vendor adds some AI functionalities. Everybody wants to take a piece of a big NVIDIA cake, I would say.
Yeah, that's fair.
And it makes absolutely sense. That's a really forward-looking application, and we see more and more that edge devices cannot just, let's say, execute some AI stuff. It also they're coming more in the range of performance that they can even learn at the edge somehow. So small steps, but we will see much more, let's say, local stuff, and the technology is there or is about to come, and with this, you can keep the processing part more to the edge, and there will be more and more processing requirements for sure.
It's interesting to think about doing not just inferencing at the edge, but also like model training. Is that what I heard you say?
To a smaller scale, actually, it's possible, or at least what's possible right now is to do the, let's say, data collection here, to have data for model retrainings or improvements. Actually, that's also the thing. But as you see that the algorithms and the stuff gets better and less performance demanding. So that's what we have seen with the large language models, that it's more and more possible to run these large language models locally. And it's also made up more, let's say, generative AI, which becomes possible at the edge. And of course, this training might be the next thing, but if you look to some announcements about compute power for module edge devices, there are some announcements. I don't know whether that really come to place or not, or which are in the, let's say, thousands of tops actually for the future. If we're then, of course, local training will become possible. So on one hand, it's a performance, and the other hand, the algorithms get better. So just think about the algorithms for AI, which we have today, have been thought about in the 60s. So, and now we have the platforms to run it. And I believe that something else was developed since the 60s here in the brains of the genius people here. And with more compute power, this can come to place. Actually, we will see a lot of new things coming.
Yeah, we have 60 years of backlog to work through.
Yeah,
we have compute. So what do you feel like is next? Can you kind of put on your Nostradamus future-looking hat for us? Where do you see this world going in the next, 10 or 50 or 100 years?
We're not talking about politics, right?
No, please no.
Of course, what I'm seeing is that the performance levels goes on and on. But what we also see is we get closer to come to more physical limits here of silicon, actually. So we already have structure sizes which are incredible. I learned at university that we cannot go below 100 nanometer, because that's technically not possible. Now we're at 2 nanometers or so.
Yeah.
So of course we're pushing the boundaries, but finally in the subatom sizes things get complicated. And also here with the performance levels, So maybe electricity is no longer the thing. We see a lot of quantum computing actually. So that's research going on. So we see computing here on optical base. So I'm following that things. It's still too early for, let's say, products in the environment, in the embedded environment here. But here on the research and on the high data center stuff, it's coming. And I see this quantum computer. So there are big progress in there. Quantum computers won't make sense for embedded computers for a while, but they have to be prepared for, because quantum computers are so powerful to crack passwords and to open security, to use this power to break into systems. That's a big thing. So that means all this cybersecurity stuff must be at a high level, and I see the point that we have to improve even much more here on the cybersecurity part for the embedded devices, for the edge devices. Because if there are more and more quantum computers also in bad hands, it will be used for bad things.
Yeah, I think history tells us that there are two sides to every coin there.
Always there are two sides. There's always a race between the good and the bad.
Let's shift gears a little bit. Can you tell me more about the origins and the kind of the foundation and growth of Congatec? How did it come to exist? What were the motivating factors?
Because it goes back here to Jumptech, that company I mentioned before, which started ETX. This was let's say 60, 70, 80 people company, which then finally got acquired, or in fact it was a merger of stock merger, to the majority of Control. So we came back to Control. My first employee, and I was back at Control, whatever. And of course, let's say having a small, very dynamic and motivated team at a pretty large company, more concern-like orientation, a lot of internal fights between departments and whatnot. That's what living in large companies is about, actually. And of course, the small, motivated team after 2 years was kind of demotivated that some things simply have not been possible, because it's some structures are carved in stone and whatnot, and then a few people decided, why not do something like Jumptech again? And then we have been 13 people. We found private investors actually, which believed in this idea actually, and then we just did it. Actually, it was the most fun time, I would say, in my professional life, actually, being a small team of 13 people. So you know everything about it, every up and down thing and whatnot. It was challenging, but everybody fully motivated, full on, and it was to create something from scratch, actually. And looking to the Congatec of today, looks like we've done something right.
Were there any surprising challenges as you spun up the new group? Any roles or responsibilities that you never thought you'd have, but then you found yourself doing that job?
Of course, first surprise was me being first CEO of that company, just as interims, actually, just to make it start off. I don't know what I signed, a lot of contracts and whatnot. So, of course, a lot of things. I'm doing an engineer, starting a public company at the time as an AG, not yet traded, but from the public form, was kind of challenging. And of course, some key learnings. So things are not as easy as they look. Our first design totally failed. Not because of we did fail, but we chosen a processor which was new and announced. It was spectacular and nice. We did a design, and then the chip vendor said, we don't do that anymore. Actually, we stopped this product line. So just when we had been ready to start our first marketing campaigns, that product was cancelled. That was the first design. It was a big disaster, of course. Yeah, but that makes you harder, makes you stronger. And another key learning was that getting engaged with large customers, being as a startup, is easy, but really they loved us, actually. That cool team, you're good technology, you're great, but I'm buying at a large company. That's the thing. Large companies buy at large companies somehow, and So I will buy from your side once you're a little grown and it's more safe to buy on your side. That I can be sure that you're in place also next month. Things like that. It took a while, and even let's say companies will say, yeah, of course it's easy. We have some relationships and we will bring them on board. They will buy from us. It took about 3 years before they really started to buy stuff from outside. So it took much longer than expected. It was a hungry time, but we've been a motivated team. That's so much.
Yeah, for sure. I think the best moments of my professional career have been with small, motivated teams, and
Yeah,
being able to build that
it's
at
so much fun.
scale or inside of an enterprise organization is a
I
special
still
thing.
remember our first trade show. It was 2 months after we founded the company. We had no product, just one piece of paper, which was our product idea, was the XTX I mentioned before. But we had a cool booth, we had a bar, we had drinks, and we had some conga drums. We made noise,
Yeah.
and they were big fun actually. Everybody was curious. Who are those crazy guys? Yeah, it was a perfect start. It was in the press everywhere actually. So a new embedded company, and these guys started their thing, got their ideas. It was a perfect kickstart.
So obviously it worked, and you alluded to this earlier. Congatec started with 13 employees, but since then you've scaled up significantly. What does Congatec look like today?
We didn't as close actually. I think we're something in the, I don't have the detailed number. We're something in the range of about 400 people. We're shipping more than 500,000 computer modules a year. So it's hard to believe because we don't have our own local production. Actually, we don't see that. But it's just think about how much boxes are those. So,
Yeah.
what's the height of the tower you can make with all the boxes of those modules actually? And now with our recent acquisition here with JumpTech, that's the module part of Contron, yeah, which was branched out actually. So we're definitely number one in the embedded computer module market. So I think it's a market share of 25% or so. Every fourth module is coming from our side, which is that's great. And with this, we have much more resources. We can do much more, let's say, custom designs. We're much more focused on this software stuff like cybersecurity things, all these tools, all these development procedures in place. I think we have a perfect position for further growth, actually. The whole market is growing. So looking the computer module market, looking to some market surveys, it's depending what you're looking, 10-15%. Everything which is AI oriented is much faster in double growth. Say you see some numbers of 30% growth rates, whatnot. So it's incredible what's going on. And I think it's right timing to add those resources to grow further.
So as people are looking to grow and they're saying maybe it's time for some embedded computer, it's time to upgrade my, strategy or the modules I'm using. What are some things engineers should think about as they're starting to develop for, one of these COM boards? What are characteristics of people who do this really well, and what are some characteristics of people who should maybe kind of rethink their approach?
Of course, if you do everything by yourself, making, let's say, your dedicated, customized computer board by self based on chip level, maybe you're too inflexible and too slow. I remember a customer which did that, and he was only able to do, let's say, a new design every 3 or 4 years. This was something like a old PC user interface thing. And with this, he had 1 year, he had a up-to-date product, but second year was already a little old, let's say, and then it was hard to sell. It was a kind of sawtooth curve actually. And then he changed to computer module concept, and now he can upgrade every year. It's just by changing a module. So you just select, let's say, one of the standards is, you name it, is it SMARC? If you stay more in the low power range, so SMARC is limited to something like, let's say, 15 watt or so power consumption, which means you're limited to some ARM or Atom platforms somehow. You cannot scale up to the higher core levels or whatever, Xeons or whatnot. So that's just not possible. If you need that, then Smart is not your thing. Then, of course, then you can think about using ComExpress. If you're okay with, let's say, medium range of performance and PCI Express Gen 4 maximum, got upgraded, by the way, then you're fine. But if you want to have a more outlook here, more future-proofness, so ComHPC would be the right one. And within ComHPC, it's, again, the thing with the small one, the Mini, which is also limited from the power envelope somehow from the interfaces. Maybe it goes up to 50 or 70 watts or so. In theory, you can go higher, but you can't cool it anymore. Or to a client or to a server. At least you should have an idea about your RAF performance envelope. And then you're safe. You want your carrier board, and then you can upgrade, let's say, with every generation, or downgrade or scale up and down, having one carrier board design and a complete product family. So let's say a entry level with let's say just a quad core CPU and then a 20 core CPU for your high end also. Something like that. All of that is possible. And I think that's the most clever thing. It's faster, it's easier, and you don't depend on a single supplier. You can change. So maybe if you're not happy with Intel or AMD or whatnot, you can change to any ARM vendors or so. Things are changing. And by the way, ARM is getting more and more attractive. So it's, as I scaling up, it's no longer just for the low end. So in the medium performance range, they're doing quite good. And also those guys add a lot of AI accelerators to it. Just have a look to NVIDIA. What's they doing? Crazy.
So what I hear you say is the people who are doing this best, and your recommendation for people who are starting to maybe implement these things, is to think flexibly and essentially like accelerate your design timelines by using these modules instead of trying to do it all yourself.
Yeah, it's in fact maybe the first design is a little effort, of course, to create your carrier board, but you can use this for multiple generations actually of CPUs, which means and it could be even cheaper. You can think, of course, I need 2 boards and connectors. It must be more expensive, which might be right as a first thought. But then think about with this high-speed stuff. See, the high-speed stuff is just, let's say, is mainly on the small board. That's where the high-density parts, or maybe you need a 12 or 14-layer PCB. The carrier board could be kind of easier, maybe 4 or 6 layers are okay. But if you make a large board with this high density components, you need these 12 layers to break it out. So a large 12-layer board, or a small 12-layer board and a large 6-layer board. I think it's a clear calculation.
Yeah. Yeah, I know, like, if you crack open one of the oscilloscopes behind me, you'll see a really high tech, carrier compute board that's where kind of the ASICs are. And then you have for the front end system, it's a lower technology node.
Could be kind of easy in a kind of cheap PCBs at the end, and the identity part is usually the smaller module. Yeah, you're absolutely right. You see this at other technologies as well, like scopes and whatnot. Yeah.
So we're nearing the end of our hour. This has been great. We like to do some lightning round questions at the end of these. Question number 1. If you could build kind of a Mount Rushmore of standards, so of different specs and standards, kind of the greatest 4 of all time, which 4 would you pick and why?
Always the latest, I would say. Nah, maybe not. I think ETX was great because it was the foundation. Even I think we still ship a few of those actually, but it's no longer important these days actually, just for legacy things. But ComHPC, in fact, is the top and followed by Smart. It's always the latest and greatest. Things like ComExpress is great. It's the most selling one, but from my point of view, it already is as its maximum. It will stay there for quite a while. I think in 10 years we will still ship a lot of ComExpress modules, but everything which is new and performance oriented goes to ComHPC. Everything which is really low power goes to Smart. So I think that's kind of clear.
Okay, perfect. If you could change a fundamental rule of physics to make something easier for yourself, What if you had like a magic wand to wave and change the law of physics? What would you change?
Maybe it's, let's say, to have some let's say, small structure transistors based on light.
Ooh, that's a good one. I like that.
Because that's how to run this computers not on electricity, or to run it on light, so you see computing on actually that's what engineers are playing with actually, so scientists are playing with it, but to really say they have been able to make something which is quite big actually, but to really bring it down to the level where silicon actually is, to a structure level closer to the silicon level, and this is what really boosts everything. And also in that performance wise, this signal integrity things might become much more easier than if it's just on light. I can imagine this would have been a good thing. Yes.
That's a really good one, and that spoken like someone who's dealt with a lot of thermals and
yeah, that's also it's energy wise, and that's also good for the environment to bring down the energy. That's also a motivation really to bring down the energy footprints. What we're seeing right now with all this AI data centers, it's relevant to the world energy market actually. So it's crazy, this AI data centers. And I'm hoping that the power consumption of those data centers can be brought down.
Well, we are out of time, but Christian, this was so much fun for me. Thank you for being here today.
I really enjoyed it. Big thank you to you.
That was Congatec's Director of Market Intelligence, Christian Eder. And this keynote was brought to you by Mouser Electronics. Delivering the newest electronic components for design, Mouser is your global authorized distributor for millions of components from over 1,200 leading manufacturer brands. Jumpstart your designs at Mouser.com. The All About Circuits Summit series happens each Wednesday in October, and sessions will be available on demand. Today, coming up, we're talking all about embedded and edge compute, and have live sessions exploring medical imaging